Good morning. So a few things is that the last time I forgot to put the dates of your quiz on the syllabus. Now I put it there. The dates are 2 in October, 2 in September, 2 in October. Okay. You can see that dates. I missed that, I'm sorry. So September 11, September 25th, and October 9th and October 23rd are the 4 days for the quiz. All right, so let's get started. And today we are going to talk about basic properties, some basic properties, notations, Bayes theorem and the posterior distributions, followed by independence and concept of exchangeability. So these are the concepts we are talking, and this is in chapter 2 class note. Before we start actual Bayesian analysis, apply the Bayesian concept to get the solution, we need to do some groundwork. We are doing that groundwork now. Okay? So today and possibly Friday, we'll do the groundwork before we move to actual model where we apply the Bayesian technique. Otherwise, we'll start chapter 3 today. So we talked about some random variables. Random variable could be a discrete random variable or a continuous random variable. And these are the notation and the basic properties we talked about in this table is the expectation calculation and the variance calculation. How do you calculate expectation? If you know the probability mass function of a discrete random variable, you just multiply the probability mass function by the corresponding value of the random variable, then sum over all possible values. This is how you get the expectation. For a continuous random variable, you don't do the sum, you replace the sum by an integration, and then you calculate expectation. All different moments can be calculated in a similar fashion. For example, if you want to calculate variance of a random variable, variance involves expectation of square of the random variable minus expectation of the random variable square of it. So it involves the second moment, and second moment's calculation can also be done by the same method that you applied for the expectation calculation. And in this class, when you talk about distribution, generally this distribution refers to the probability distribution. So suppose I say the joint distribution of random variables y1 and y2 is p sub y1, y2. It implies the joint probability distribution, density function or probability mass function. So if y2 is a discrete random variable, then the marginal PDF or PMF of y1 can be obtained by summing over all possible values of the discrete random variable y2. And this is the notation p y1, y2. This is the joint distribution of y1, y2. And I'm summing over all possible values of y2. And this is the notation, summation notation. If y2 is a continuous random variable, then we replace that summation by an integration. So this sum is replaced by an integration. This is the integration. If I'm interested in the conditional distribution of y2 given y1, this is the notation p sub y2 given y1, and it can be obtained by this ratio. the numerator is the joint density function of y1, y2, and the denominator is the marginal density function of y1. Okay. For a discrete y2, this conditional density of y2 given y1, if I sum over all possible values of y2, it will always be equal to 1. And for a continuous y2, we replace the sum by the integration and it will still be equal to 1. So my point is the conditional density, when you have the conditional density, it behaves like a probability density function. It's a probability density. So if you sum over all possible values of the random variable, you get 1. For a discrete variable, for a continuous variable, you do the integration. And if there is no ambiguity, we will drop the subscript to write probability Py1 to denote the marginal probability for the random variable y1. Similarly, we'll be using Py1, y2 to denote the joint probability of the random variables y1 and y2. Conditional expectation is defined as follows, and for the conditional expectation calculation, you need the conditional density. And if y1, y2 are independent random variables, then the joint probability density of y1, y2 can be obtained as the product of the two marginal densities. Now, why I talked about this? Because these are bread and butter of the Bayesian computation. You'll see we are using this concept again and again for any problem. That is why it is better that we have a clear idea about the notation and the quantities we are going to compute. Another thing is, suppose I'm interested in calculating the sum of two random variables, y1 and y2. Expectation of the sum of the two random variables. Now, in this calculation, do I need to obtain the density function of y1 and y2 in order to calculate the expectation of y1 plus y2? No, I don't need the joint. I don't need the density of y1 plus y2. As long as I know the expectation of y1 and expectation of y2 separately, then I can do this calculation simply, just adding the two terms. Now, why I spend so much time on this simple formula, very simple formulas, because in my class, there are a lot of students who do not have statistics background. They are coming from a different background. So what we take very obvious, straightforward, that may not be obvious to other people with other background. That is why I'm spending time to make sure everyone is on the same page and understand the notation and the basic properties of some of the calculations. Okay, and in this calculation, if I want to calculate expectation of y1 plus y2, I do not need the independence assumption of y1 and y2. I do not need the joint distribution. I do not need to know the joint distribution of y1 and y2. As long as I know the marginal expectation of y1 and y2, that is sufficient. Another concept we use very often is proportionality. So a function fx is proportional to gx, denoted by fx, this notation, proportional notation, gx, if we can write fx as a constant c times gx. C times gx. And in order to make fx a probability density function, what you need is fx must be greater than equal to 0 and integration of fx over the entire domain of the random variable must be equal to 1. So with that restriction, we can calculate that proportionality constant C, as long as you know Gx. So here is an example. Consider the standard normal distribution. So suppose I have a random variable y that follows the standard normal distribution. Normal distribution with mean 0, standard deviation 1. So its probability density function is the following: Py equal to 2 pi to the power minus 1/2 e to the power minus y square over 2. But I can simply write this guy as e to the power minus y square over 2, ignoring the proportionality constant. That is why I wrote this symbol, proportional symbol. And as long as I know that the density is proportional to this, it is very easy for me to figure out this part, constant of the proportionality. Now, let me give you another example. Suppose I know fx, suppose the probability density of a random variable fx is proportional to e to the power minus x squared over 1.5. Then do I know the constant of proportionality? Yes, I can easily figure out the constant of the proportionality. Why? Because I can write first fx equal to c times this guy e to the power minus x squared over 1.5. And then I know this rule because it is a probability density function, the integration of fx equal to 1. So it is c times the integration e to the power minus x squared over 1.5 dx. So what it means c equal to 1 over this guy. Okay, and this integration is from minus infinity to plus infinity. And this integration, using the gamma integration, one can evaluate that. And it becomes square root of 2 pi times 0.75. 0.75, why? Because the rule is the following: e to the power minus infinity to plus infinity, e to the power minus x squared times 2 times sigma square equal to square root of 2 pi sigma square. So what? I wrote this 1.5 as 2 times 0.75. Therefore, I got this expression. Okay, so I got the proportionality constant C. And it is simply the integration of that gx function over the domain of the random variable. Now, basic Bayesian inference. Suppose we are to observe a vector of data y, and its realization is denoted by this lowercase y, and y has a probability density function that depends on some unknown parameter theta. And let us denote this by py given theta. Now, in the Bayesian inference, what I told you is that we need two input. One is the probability model of the data. Another is the prior model or the prior distribution. And if I put these two, then the outcome will be the posterior distribution. Use the posterior distribution for statistical inference. Okay. You can use the posterior distribution even for forecasting of a future observation. So the basic output from the Bayesian machinery is the posterior distribution. So this is a problem in the notation. I made a mistake here. We'll denote the distribution, the prior distribution, by pi theta. And here I have used p theta. So this is my mistake. I will correct this. And if this is A is a region, then integration of this pi theta d theta will represent the probability, prior probability that theta is in the region A. Now, let us calculate the posterior distribution. Posterior distribution of what? Posterior distribution of the parameter theta. Theta is the unknown parameter I told you. We assume the data generating model given the unknown parameter theta. And we want to make inference about this unknown parameter theta through the posterior distribution. So pi theta given y, this is the, you can think of this is the conditional distribution of theta given the data. It is the joint distribution of data and theta divided by the marginal distribution of the data. Okay. And the joint distribution is written as py given theta times pi theta. And the marginal part in the denominator is written as py given theta pi theta integrated over theta. Now, do you see the similarity between this formula and the Bayes formula? So the Bayes original formula was not written for a continuous random variable, continuous distribution, but they are very analogous to each other. Look at this. In the Bayes formula, the conditional probability of AJ given B was given. So in our context now, B is your observed data and AJ analogous to theta, unknown parameter theta. And in the numerator, you have B given AJ. B is our data Y given parameter theta times the probability for theta, pi theta. And the denominator is the marginal probability of B, which is analogous to our data. This is the connection between the posterior distribution or the posterior density and the Bayes rule. So now what you see is pi theta given y has the numerator and the denominator. And now I write this is proportional to py given theta times pi theta. Why it is proportional? Because the denominator, look at the denominator. Does it depend on theta? After integrating out with respect to all possible values of theta, it is free from theta, right? It is a constant term. That is why I wrote it proportional to the numerator part. And this is a beautiful thing. Actually, to enumerate this distribution pi theta given y, I do not need this constant of proportionality. It is very difficult, first of all. Constant of proportionality calculation is very difficult. If it is a scalar theta, you can do integration. But if it is a high dimensional, multi-dimensional thing, then this calculation is not at all easy, and difficulty increases depending on the data likelihood. If the data likelihood is not a standard likelihood, it's a very difficult computation. So we completely avoided this difficult computation for the time being. If you want to evaluate only the posterior density function. Later on, we'll see that sometimes we need to evaluate this proportionality constant, and to do so, we have a different technique. So the bottom line that you get is that the posterior density is proportional to the prior density function of the parameter and the data likelihood. Data likelihood means the density function of the observed data given the parameter theta. Now, I apologize to you that I'm mixing up the notation P and pi. P here, it should be pi actually, and this one should also be pi. I will correct that. But I'm sure you guys understand that it should be the prior distribution and the posterior distribution I'm referring to. So what you see is that the posterior distribution depends on the prior probability. So if I use one prior distribution, I get one posterior distribution. If someone uses some other prior which is completely different from my prior distribution, their posterior distribution likely to be very different, right? So there is a subjectivity. In Bayesian analysis, it can change from one subject to another depending on the choice of the prior distribution. But there are some safeguards we can apply, and that is called objective way of analyzing data. That is called objective Bayesian method, where we will not choose the prior distribution subjectively. Another thing is, if the two prior distributions are not widely different, and if you have sufficient data, then prior distribution will have moderate to minimal effect on the posterior distribution. But if you have only limited observation, limited number of observations, then prior distribution will have huge impact on the posterior distribution. All right. So now let's talk about conditional independence and exchangeability. So two events A and B are independent, written as A perpendicular B if probability of A intersect with B equal to probability of A times probability of B, if two events are independent. If two random variables are independent, it means the joint density function of these two can be obtained as the product of their marginal density functions. So what it means? Independence means happening of one event has no information on the happening of the other event. In other words, even if I condition on the fact that B has happened, probability of A remains unchanged. So probability of A given B is equal to probability of A. Similarly, probability of B given A is equal to probability of B. If two events are mutually exclusive, keep in mind, then they are not independent. Two events are mutually exclusive. That means one event and the other event cannot happen simultaneously. So if you know one of them has already happened, that means the other event has a zero probability of occurrence. That means what? Given the information of one, you know the probability of the other, which is different from the marginal probability. Two events A and B are conditionally independent. So far we talked about two events A, B independent. Now we talk about conditional independent. So conditional independence given another event C means given C, A and B are independent. And in probability, it will be probability of A intersect with B given C equal to probability of A given C times probability of B given C. Another thing, as a consequence of that, if this happens, then probability of A given C intersect with B is probability of A given C. So in other words, knowing C and B gives no extra information about A other than C itself. This concept, conditional independence, will be used again and again in our Bayesian analysis. So we say random variables y1, y2, yn are conditionally independent given the parameter theta if for any collection a1, a2, an of sets, the joint probability of y1 belonging to a1, y2 belonging to a2, so on and so forth, given theta, can be obtained as the product of these conditional probabilities that yi belongs to theta ai given theta. So if that happens for any collection of a1, a2, an, then we can write the joint density function of y1, y2, yn as the product of these density functions. Now, in the classical inference, we say observations are independent. Suppose I say y1, y2, yn, these are the observations collected from a population and they are independent. But in the Bayesian analysis, you have to keep in mind that the parameter of the model is a random quantity. So our statement should be y1, y2, yn are independent, conditional on the given parameter, because parameter is a random variable. Exchangeability random variables y1, y2, yn with joint density p y1, y2, yn are called exchangeable if probability y1, y2, yn is same as probability y pi 1, y pi 2, y pi n. Now what is this guy? This is a permutation of these values for any permutation. So for an example, suppose n equal to 2, I have two observations, y1 and y2. They are exchangeable. What it means is that the joint probability that this first random variable equal to little y1 and the second random variable equal to little y2 is same as the joint probability that the first random variable equal to little y2 and the second random variable equal to little y1. So what it means? It means the ordering of the data conveys no information other than the observations themselves. Can you tell me where this ordering is very important? In which context? time series, exactly. Because there you cannot say y1, y2, y3, they are exchangeable. So exchangeability is a concept. I'm not saying it will hold everywhere, but if it holds, that means ordering will not have any impact on the likelihood part. Now, conditions for exchangeability. Suppose that y1, y2, yn are independent and identically distributed with common marginal density F, then the joint density P of y1, y2, yn is this, because I said independent, they are independent, right? So if they are independent, their joint density can be obtained as the product of the marginal density functions. Now, because of the commutative law of multiplication, y1, y2, yn are exchangeable. So if I write, let me tell you this one. Suppose I consider n equal to 2. Okay, I have two observations, two random variables, y1, y2, and they are IID, independent and identically distributed. Question is, if that is the case, are they exchangeable? So the joint density y1, y2, y1, y2, instead of writing y1, y2, I will write the two values as R and S. Because of independence, it is y1 marginal density evaluated at R and the marginal density of y2 evaluated at S. And since they are identically distributed, I do not need to write Fy1, Fy2, I simply write Fy, okay? This is because identically distributed observations. And this is because of independence. IID. Now, is it exchangeable? I can write also y1, sorry, y s r, and I can simply write it as s and y2r, and I can write it as y1, y2, s and r. So look at this ordering R and S, and this is S and R. They are identical. That means in this case, if the observations are IID, they are exchangeable. I showed you using n equal to 2, but same idea applies for other n. So if y1, y2, yn are identically distributed and unconditionally independent, that means they are independent, okay, without conditioning on anything, then they are exchangeable. But exchangeability does not necessarily imply unconditional independence or independence. And here is one such illustrative example. Suppose that two random variables, y1 and y2, have the following joint density function, okay? And the density function looks like this: e to the power minus c square plus d square minus cd over 1.5. Observe that the density is exchangeable. Obviously, if you swap the position of C and D, instead you write D comma C, the density function remain unchanged, right? On the right side is the same. But what about conditional independence? Are the two random variable conditionally independent or unconditionally independent? So first, it can be verified in many different ways. I will do the following. I will calculate the marginal density function of y1, and I will check if the marginal density is same as the conditional density of y1 given y2. If they are, then they are independent. If they are not, that means they are dependent. And marginal density of y1, how do you get it? If you know the joint distribution, this is the place where we apply the rule that I showed you early in the class. So you have the joint density function of y1 and y2, and you integrate out the second random variable to obtain the marginal density. So this joint density is proportional to this expression. It is given to you, right? Given to you. And I'll be integrating with respect to R. So any term which is independent of R, I take it outside the integration. So I take out this part, the first term. And for the rest of the part involving R, what I do this one. I have R squared term and minus C times R term. I do the square completion. Now, this is another important thing. To do integration of something which is like e to the power minus x squared and a linear term. If you have that, then you can do the integration. If the range of integration is minus infinity to plus infinity, you can do that integration using normal density integration. And there, what you need is a square term, complete square term as a power of E. And that is why we call it square completion. So what I did, R squared minus 2RC. You see how I wrote R times C as 2 times R and C over 2. Now, in order to do C over 2 term here, I need to bring in the C over 2 square, right? And this is an extra term. So and also it has a denominator like this. So I put it outside also, this C square over 6. This extra term I bring in and also subtract it. So now this part becomes R minus C over 2 square, and in the denominator you have 2 times 0.75 dr, and this integration is a normal density function integration, and it becomes square root of 2 pi times 0.75. So I don't care about this part much, okay? This part I don't need to pay much attention, the exact value, numerical value. But what you see is that the marginal density is now proportional to e to the power minus c square over 2. What is that density? If it is proportional to e to the power minus c square over 2, It is the normal density function, right? Normal distribution with mean 0, standard deviation 1. This is the essence of this calculation. Next, conditional distribution of y1 given y2. Do I need to derive the conditional distribution? No. You see, I told you about the proportional symbol, right? So conditional distribution of y1 given y2 is the joint distribution of y1, y2 divided by the marginal density of y2. But in order to figure out how the conditional distribution depends on C, I just need to look at the numerator, because the numerator only involves C, the argument for the first random variable. So I just simply write it proportional to P y1 comma y2. And that thing is this. And I can write it nicely as C minus 0.5 r square, okay, 0.5 r square divided by 2 times 0.75. Therefore, the conditional distribution of y1 given y2 equal to r is a normal distribution with mean 0.5 r and variance 0.75, which is clearly different from the normal distribution with mean 0, standard deviation 1, marginal distribution. So what do you prove? You prove that here exchangeability does not imply independence of the two random variables. Now you may wonder how I got this one. Okay, remember I did not write P y1 y2 cr exactly equal to this expression. I wrote proportional sign because in order to write this 0.5 r square, I brought in some extra r term, r related term, but that r related term is absorbed within the constant of proportionality. It does not depend on C. C is our main argument. All right. So it's a very general advice I have been giving to all the students, and nowadays it is more important. Nowadays, you see, before coming to the class, I always practice by writing, right? Same thing, I will advise everyone to practice by writing on a paper pencil, not just looking things on the computer screen. If you see things on the computer screen, it does not go in my mind. And when it comes, oh, so for your class, there is no writing part, right? That is a nice thing. But if you really want to learn the subject, although it is not required for the assessment, if you want to learn something, you have to practice by writing. I forgot completely. The assessment procedure is quiz, which is online. You don't have to write anything. And exam online, and project writing, that is online, where you can use OpenAI, ChatGPT. But before you submit, make sure it looks like, the project looks like a real person wrote it, even though you take help from ChatGPT. It does not mean that you add some mistakes there, okay, typos. Nowadays, people are doing that because it's so perfect, they're adding some mistakes. No, you're writing, I can clearly see which one is written by, I mean, I can understand which one is written by OpenAI and which one is written by a human being. All right, so we did, yes. So if y1, y2 are conditionally IID given theta, then marginally y1, y2 yn are exchangeable. Okay, so this is another thing, conditions for exchangeability. If y1, y2, yn are conditionally IID. So previously I said they are independent and identically distributed. I did not say conditionally. This time I'm adding extra layer. So given theta, they are IID. Then marginally y1, y2, yn are exchangeable. Now to see that, suppose I have two observations, n equal to 2 and y1 and y2 are conditionally IID. Then their joint distribution y1, y2 r comma s is equal to the joint distribution given theta times pi theta. What I told you is that these two guys are conditionally independent. That means you can break it up as follows. The density of y1 evaluated at r given theta and density of y2 evaluated at s given theta times pi theta. And because these guys are IID, I can switch the position of R and S. I just write S and R, and then write again the joint density S and R. It becomes the joint density of Y1, Y2 evaluated at S and R. So this is what happens. The ordering will not have any bearing on the density function, joint density function. We started with R and S. We end up with S and R, same thing. And that is what exchangeability means. Questions? Questions? So what we learned in chapter 1 and chapter 2, the basic concept, basic calculations, we'll apply these in chapter 3. Chapter 3 starts with one parameter model, such as one parameter model like the binomial model, like the Bernoulli model, right? So there is only one unknown parameter, success probability, or the Poisson model, where the rate parameter is the main quantity, generally unknown, and we want to make inference about that. So one parameter model means you have collected data and you assume that data are coming from one of the models, either the binomial model or Bernoulli model or the Poisson model. You assume that, but the model parameter is unknown. You want to make inference, Bayesian inference about that unknown model parameter. Okay, so this is the topic of chapter 3. So we'll start with the Bernoulli and binomial experiments. So in a Bernoulli, and these two guys are so connected, so closely connected, Bernoulli and binomial. So there are two possible outcomes in a Bernoulli experiment. One outcome, we call it success. Another outcome, we call it failure. Okay. And success generally denoted by 1 and failure by 0. So for a Bernoulli random variable, the random variable takes two possible values, 1 and 0. 1 with probability pi and 0 with probability 1 minus pi. Okay, so this is an example. Suppose this is glossophobia example. Suppose that we randomly pick one student and check if the person has glossophobia. Okay, why is it a random variable? Because if I pick one person at random, that person may have glossophobia, may not have glossophobia, right? And that whether the person has or has not depends on the random person I'm choosing. That is why it is a random variable. It is not fixed. So it is a Bernoulli random variable. Okay. So Bernoulli random variable. A binomial experiment consists of a sequence of independent Bernoulli trials. Each will result in 0 and 1, and each trial is independent, and the success probability of every trial is the same. If these conditions hold, then we call it a binomial experiment. So binomial experiment consists of independent and identically distributed Bernoulli trials. Therefore, Bernoulli and binomial are so interconnected. So we'll talk about this glossophobia example in the binomial distribution context in the next class.